solving trig equations within one rotation using the factoring strategy. One of the things that you're going to want to do is, before moving forward this video, make sure that you watch the previous videos talking about how to solve using inverse operations, how to find principal roots, and also going way back to the quadratics, how to factor in general. We're going to move forward as if all that is information that you're comfortable with, but again, if you have difficulty, maybe revisiting those videos could be a good starting point for us. In this first example, I want to go ahead and be able to see what significantly tells me that I'm going to factor. And what I see in this case is the fact that I have two different trig functions. I have secant and I have cosecant. That's usually a red flag whenever I see two different trig functions pop up that I'm going to be using a factoring strategy. And the factoring strategy I'm going to do in this case is factoring out a GCF, or greatest common factor. So I see both have a GCF of cosecant x. And upon factoring out a cosecant x, I get the following statement. I get cosecant times secant x minus 2 equals 0. Now from here, this is nice because now I can use that zero product theorem. I could say cosecant x equals 0, secant x minus 2 equals 0. From here, I got to solve each one independently. So in this first one here, I have cosecant x equals 0. So I have to remember cosecant is the reciprocal of sine, which is actually going to be r over y. So in order for this to be equal to 0, I have to know that cosecant, cosecant's going to be equal to 0 if and only if r is equal to 0. Wait a second, maybe cosecant can't have, so there's no real solutions to this. Because we're always going to have some distance of a radius, so we can't actually be equal to 0 there. So I don't have to worry about working with that first one. In the second expression, I get secant x equals 2. Secant's the reciprocal of cosine, which is our x-coordinate. So x is positive here and here. I'll know that r is 2, x is 1. So then that's going to tell me I'm using pi over 3, which furthermore, I know x is not only pi over 3, but it's going to be this angle here, which is going to be 5 pi over 3. So a lot going on in this problem, but the very first thing is we had to factor it, and then from the factoring, we had to set up our two different scenarios to come up with our final solution. Let's take a look at the next problem. Something that's significantly different in this next problem is the fact that now I have the same trig function. But what I can see is I had the same trig function, but I'm raised to a power of 4 and a power of 2. So in a very similar way, I'm going to factor out a GCF in this problem. So my first step here is going to be factor out a cosine squared. Now again, I have a factored form equal to 0. I can use that zero product theorem. I get cosine squared x equals 0. I get 2 cosine squared x minus 1 equals 0. This simply tells me that I'm going to end up with cosine x equals 0 upon taking the square root of both sides. And in this scenario, I'm going to get cosine x is going to be plus or minus square root of 1/2, or in other words, plus or minus 1 over the square root of 2. All right, so now we have to go ahead and solve both of these scenarios. I understand that cosine is the x-coordinate, so the x-coordinate is going to be equal to 0 at pi over 2 and 3 pi over 2. And then in our second expression, we end up with the following. We're going to have all 4 quadrants occupied. So if I just represent the 1, this is going to be 1 square root of 2, which is my 45, 90, which is going to tell me x is equal to pi over 4, 3 pi over 4, that's going to be that angle, 5 pi over 4, and 7 pi over 4. So in this second problem, now you can see we actually have 6 solutions. We got 4 from our factor of 2 cosine squared x minus 1, and 2 from the cosine squared x being equal to 0. So one of the things that we see here is we tie back to a lot of our previous knowledge, but before we get into our comfort zone of being able to solve with inverse operations, we first have to get that factored form and apply that zero product theorem.